The next presenter is Robert Mistrick, with the title of the presentation is Development and Utilization of Cloud-Based Library for Unknown Consonant Identification. Please go ahead, Robert.
Thank you. Thank you, organizers, for giving me the opportunity to talk at this meeting and start this compound identification session. Well, it doesn't happen very often that somebody asks a question before even the talk starts. And Professor Vienken asked a very important question. Well, we can identify a lot of compounds, but how they relate to the all wisdom from Paracelsus, we know what I'm talking about. Well, actually, we have this privilege in Bratislava that famous Paracelsus visited us. And now we try to continue in his work, and I will address the question later on in my talk. Well, you're absolutely right. We can identify a sea of compounds. So this is a plasma sample, LCMS chromatogram, and all those triangles denotes a component. It's probably a pure compound, but there may be some interferences. But you see the complexity of one sample, and of course, as low with concentration we go, the more compounds we see. So therefore, I'm absolutely convinced that in a plasma we can see much more than 800 components. Of course, depending from the extraction and analytical methods. Well, we can today identify maybe 10, maybe 15% of them. Some people claim 20%. I would be rather skeptical. But still, this is a very small portion of all compounds we can detect in complex samples. Well, if we reduce the structural space, let's say, well, look only at some pharmaceuticals in a human plasma. So this is one metabolite experiment. So those are the metabolites which were described in the literature. And if we increase these, if we enlarge this chromatogram, so we go deeper and deeper, so we see a lot of low abundant components. Well, we have here today that compound identification is a real bottleneck in leachable and extractable area. However, this problem goes through various other scientific fields, whether it's metabolomics, environmentals, and others. This is kind of a paradox because we are hearing every day that there is a Mars rover and analyzing the Mars soil. So there have been mass spectrometer on Jupiter falling down. There was a mass spectrometer on a Saturn moon and so on. Why we cannot identify the compounds on the Earth? So, and we have the sample. So we have all these instruments, and why it's so complicated. I will try to explain you why, but not to make the even complicated story even more difficult. So I will only focus on the LCMS. So I will not touch other analytical techniques like GCMS or NMR or others. Well, for many decades, the method of choice for compound identification was the library search. It still remains, is a very good technique. However, we have a very small LCMS databases. So currently, a couple of thousand compounds. If we imagine how many compounds we can search on a PubChem, it's many millions. And on the CAS, it's even about 100 millions. So it's a very small fraction of a compounds that are represented in a spectral databases. Today we have very cool techniques like high resolution method, but people and software are still using low resolution technique and low resolution thinking when using high resolution spectra. Even the library search is a great technique. It has a lot of nuances and a lot of problems, and I would like to mention a couple of them. Then we have an inherent problem with the compound identification. Well, we are actually fighting a huge combinatorics, and I will explain you what does it mean to identify a compound. It's actually to somehow get under constraint the combinatorics. Today we have two groups of compounds, known unknowns and unknown unknowns. You probably know what I'm talking about. Another problem is ad hoc identification. It's extremely difficult to identify a compound if your colleague will provide you a sample. Well, let's tell me what's inside without knowing the context. Where is the sample coming from? What's the history of the sample, and so on. So to identifying compounds without additional information is very difficult, if not impossible. And the last problem is the promises made by computer-assisted method have not been fulfilled yet. If you take look in the scientific literature, you can read about amazing method, automated structural elucidation, machine learning method, artificial intelligence use for compound identification. Well, you probably know those are overstated claims, and actually there is no automated method for structural elucidation, regardless of what you can read in the scientific literature. So, because the motivation of academics groups is a little bit different, and we have to solve the real problem. So we have a sample, and we have to identify the compounds and sign the results, and not only produced scientific papers. Well, what's the problem with the library searching method? First, spectra reproducibility. In LCMS, we can acquire spectra at various experimental conditions. One of the parameters is the isolation width. So we have here on the top a spectrum acquired at isolation window 4. This is isolation window 1.5. So you see, even though spectra are coming from the same compounds, their different spectrum is absolutely different. Neither human nor any search algorithms will recognize it as identical compounds. Second parameter is a collision energy. So we can acquire spectra at various collision energies. And what you can see here, these are those breakdown curves. This is the intensity for a particular ion, and this is a collision energy. So this is an ideal case where at every collision energy we have the same intensity. Well, the reality looks often much more complicated. So you see at various different collision energies, we see different ion intensities. So all those spectra will be completely different. So, and that's what we have to overcome. Another problem is the spectra quality. In LCMS, you have all kinds of impurities, adducts, coeluting peaks. It's not easy to get a clean spectrum, so we have to either filter the spectra or do other measures to clean up the spectrum. So, because you can see those spectra will never be recognized coming from the same compounds. Then it is a spectra specificity. Some compounds exhibit very rich, nice fragmentation patterns, so very good fingerprints. Some fragments not that really, and often they produce very trivial neutral losses like water loss. So we can have hundreds, if not thousands, compounds that will produce a water loss. So the spectra will be very similar. Not only the water loss, it's also the ammonium ion. Spectra ambiguity. We may have the mass spectrometry is a great technique because it is very sensitive, but sometimes some substructural information may be completely hidden, and this is the case. So here is a compound without a sugar moiety, and with sugar moiety, the spectra are absolutely identical. So this is a so-called dark matter in mass spectrometry. So this sugar just doesn't leave any trace in a mass spectrum. Then it is an isomer differentiation. We have two different compounds. Yes, very similar, but still different. Spectra are almost undistinguishable. So you have to be very careful if you get a library spectra as a hit. So if you get a hit list, so if first compounds, it's truly your compound. So you have to be always skeptical. Structural diversity. it's actually more intended for younger people, for students, because students don't realize how diverse our structural space is. So if we take one MZ value, for example, here, it's at high resolution, we calculate a possible molecular formula, and then we put this formula in a structural generator, so you see how many structures we can get, and the hard disk was full after 22%, so many structures. Many of them are chemical nonsense, but still you see the huge structural diversity. And this is a very small MZ values. As we go high up with the MZ value, the combinatorics get worse. Then we have an accuracy issue. I will not go to the specific, but it's also not trivial. And a spectra structural relationship, well, that's what happened in a mass spectrometer. We see only few of the peaks. Why? Because of thermodynamics and because of some structural arrangement and so on. If we change slightly the structure, maybe different fragments can be seen in the spectrum. So therefore, it doesn't mean that if we see only those peaks, that there is no other fragments. That's not true. There are many other fragments, but the intensities are different. Okay, so we try to address all the problems, and we came up with a concept called spectral trees. Spectral tree is a data structure which holds spectra acquired at various collision energy, various MS stages, and it is put under one roof. Here we have a MS1, MS2, and MS3, and maybe even a lower MSN level. Those sheets of papers are parallel spectra. Those are spectra acquired at various collision energies coming from the same precursor. And we store all this data in spectral tree. We went further, and we adopted this concept spectral trees and implemented it in a mass spectral database. So you have heard today, it's called MZ Cloud. MZ Cloud is a free database, so anybody of you can search there, so can copy and paste Spectrum or open the Spectrum and search in a MZ Cloud. It contains spectral trees, sometimes rich, sometimes we have only MS to the second spectra. And I will a little bit more introduce you to MZ Cloud. So we have spectral trees, we have associated chemical structures, we have predicted precursor structures, and we see the spectra from various contributors, because it's very important to have a spectra from different experiments, because it's better to have two confirmations than just rely only on one contributor. Then we can also display the breakdown curves I was talking about. We do peak annotations, so we have a heuristic annotated peaks and quantum chemically annotated peaks. You can see the structural view, you can see all the structures. You can search the spectra, so this is a typical search results where you see this is your hit list. Here's the match factor, and you can combine the spectra visually and also through three various matching algorithms or scoring algorithms. And it shows you in which peaks was actually found. And this is actually the biggest power of this MZ Cloud database, that we try to acquire the spectra at various experimental conditions. And the search algorithms match your unknown with all the experimental conditions and try to find the best match. So in database, we have all the information. On the experimental side, you don't need to have all the information. We will try to pair this information and to get the best match. We collect a lot of metadata, and we do quantum chemical prediction, which is actually unique for a mass spectral database. So we use internal computing cluster, and we use also a supercomputer in America, because this is a very computational demanding task. So how do we build our database? We take authentic standard, then we acquire using the mass spectrometer spectral tree. We put it in the database, and you as a user can search it for the free. So this is the current stage. We are adding 30 spectral trees a day, so in about a year we will double this number, and then we will go further. So, more detail how it works. We take the reference compound, we use a direct injection, and we have a special software that controls the mass spectrometer to create all those rich spectral trees, because our philosophy is, once we have a sample, we would like to get everything from the sample. We squeeze the sample to the last drop and get spectra as many experimental conditions, as many collision energies, as many as possible precursor ions, and deeper as possible with MSN stage. Why? I will show you later. And yeah, then we process the data and they go to MZ Cloud. Once again, so this is the software we used for generation of the spectral trees. Sometimes it takes 20 minutes. We have a spectral trees that were acquired, it took 7 hours to acquire such a spectral trees for one compound. But these will later pay off. We built really high quality database. This database is manually curated. We have 3 full-time curators who do filtering, recalibration, data processing, extracting from the chromatogram, and adding meta files to our records. So we really pay a big attention to quality. So we have here, as I mentioned to you, filtered and recalibrated. Since recalibrated are artificially changed spectra, so we better keep them separately, and you can search in both of them. So you have a filtered spectrum and filtered and recalibrated spectrum. And the search algorithms go through all of them. Why we are doing it? And actually, I would like to now talk more about compound identification. If the compound, unknown compound is in a database, so well, it's not a big deal, so we will find the compound and we have it. If we do not have the compound in the database, so we have to find with other techniques. And a decade ago, we have introduced this precursor ion fingerprinting method. This tries to identify substructures from unknown spectra based on the analogies with other spectra. It is well known that identical fragments produce the same spectrum. Why it is? Because once we isolate a fragment doesn't remember where it is coming from, doesn't remember parent. So once we isolate a fragment and do MSN spectrum, we will always get the same spectrum. Not the same, so I would rather say matching spectrum. The only thing what the ion remembers is its internal energy. And we can compensate these internal energies by spectra acquired at various collision energies. So if this one would be unknown and those would be in a database, we could at least identify the substructures based on these spectra. And this is the reason why we build very rich spectral trees, because we would like to build a database of substructures. If we cannot identify the structure itself, at least we can do substructures. The advantage of this method compared to other computational techniques you are reading in these scientific papers is we are not doing here some strange mathematics. We are actually comparing nature against nature. So we are comparing spectrum of a substructure against spectrum of a substructure. So, and this slide actually shows that it really works. So here we have a different compounds that yield the same fragments, and we have matching spectra. Another example and another example. It works well for positive and negative electrospray. So, how it would work? Well, we acquire MSN spectra of an unknown compound. We search those spectra in our library in MZ Cloud. We identify the substructures, and then we have here results. I have to admit this is an ideal case. That's not happen not that often, but at least this is the model how it should work. As more substructures we have in our database, then better we can identify the compounds. So, and this is how it works experimentally. So we acquire using Orbitrap and tree robot spectral tree. We search the spectral tree, put in the database, and we can identify the substructure. Of course, the identification success is heavily dependent on substructures we have in our MZ Cloud database. And we try to cover all application areas, so we have a couple hundreds of leachables and extractables in our database. But this is also a model how you can build your own database. So because many of you are working in a relatively limited structural space, so you are not dealing with the environmental compounds, you can encounter everything. So therefore, we always recommend to build in-house database of compounds that are actually in all our company, because those substructures can be later on found in our samples. So this is an example from the metabolomics. So this is an extract from our orange. So we have an unknown component here. So this is a spectral tree. Using Mass Frontier, we have extracted the tree. Then we search the tree in MZ Cloud. So this is our hit list. And this is actually the substructure. So we have the substructure. And then we get this routine, which may be a problem because this is exactly the case I was talking about, this dark matter. But at least from total unknown, we have some substructural information. If we would search the spectrum in a normal spectral database, there would be no hit. Another example, so we have searched those sildenafils. And we've got exactly the same, using exactly the same method. This is our hit list. And another techniques, you can do also the substructure search. So you can do it in a reverse order. So you actually search based on substructure search what kind of spectra I would exhibit in my sample. We moved this story a little bit further. And as I mentioned to you, we do also the quantum chemical predictions. We take chemical structures and we try to calculate the fragment stability and to get really high quality information about our fragments. So here you see the relative electronic energies for all the fragments, and of course the lower the relative electronic energies, then more stable the ion is. Since we are using different quantum chemical techniques and every technique gives you a different answer, so therefore we show those level with those different colored lines. So this is the most likely fragment. You see, you can preview all those methods on MZ Cloud. Since this is not binary logic, the fragment is this one and no other, so it's always a statistic and probability. So you see the probability for each fragment that we are calculating, so you can preview it there. You can see even the three-dimensional structures. So this is our typical view. Since it takes so long, it's very expensive to calculate those fragments, so we are just continuously filling this information in MZ Cloud, so you will not see all the quantum chemical calculation for all the compounds. It will take us a couple of years and a lot of resources, but we are progressing. Oops. Yeah, and red are our quantum chemically calculated fragments, and blue are heuristically calculated fragments. So those heuristics wait to be calculated quantum chemically. Why we need those high quality fragments? Well, the typical experiment in mass spectrometry is you have a MZ value, you search in a structural database, and you would like to restrict these all candidates to one or a limited number of them. Using precursor ion fingerprinting, we identified those compounds, and if we have a high quality fragments like this one, calculated quantum chemically, so we can with certain probability say this is this one. I have a few minutes time, so I would like to show you a light version of the precursor ion fingerprinting, and this is called Fragment Ion Search. This is a typical metabolite identification experiment. And how it actually works. Well, if we have a parent drug and if we have a metabolite, based on the precursor ion fingerprinting logic, they often produce the same fragments, yeah? Because the metabolized portion just went away, and we have the same fragments. So we can compare those fragments, which were calculated using in silico prediction, with the actual spectra we observed. And then we can compare it either in unit resolution, but it wouldn't work very well because of the isobaric coincidence. What we really need is a high resolution. So if we identify this peak 282 in our chromatograms, we can be sure it somehow is associated with the metabolite. So how it works, we take a parent drug, we generate using mass frontier fragments on the heuristic, using heuristic methods. Those are our predicted ions. Then we calculate MZ values, and then we search those MZ values in a chromatogram. So this is metabolite 1, metabolite 2. How it works in the software, just we take the structure, we predict the fragments, we generate MZ values, and then we search them in a chromatogram. This is a metabolite ID experiment. You can do it for any type of experiments. You try to find a relation with a compound with a complex sample. So it can be very well used in impurity search, so because you can take the precursor compounds or all the chemicals that were used to produce these compounds and search them in a chromatogram. The advantage of this method is not only that it shows you the peaks that are related with your investigated compounds, it gives you also some partial substructural information. And then you have to, I have to admit, you have to put it manually together and make sense of all these results. But at least you can see what kind of substructure belongs to which chromatographic peaks. How do we do this, this prediction? Of course, we cannot provide you a supercomputer to do quantum chemical calculation. So therefore, we have a desktop application called Mass Frontier, and Mass Frontier does this fragment prediction. Because this is for both method I've presented you, it's very important to have a high quality fragment prediction. We do it based on general fragmentation rules and based on the rules published in the literature in all scientific journals. So actually all, we cover now 95% of all fragmentation mechanisms. So we extract the fragmentation mechanism from the literature, put it in the software, and software try to find appropriate mechanism and fragment the molecule based on these mechanisms. So, and as you see, so we put everything on the paper. It's manually curated, and it is of high quality because some of the, to decipher some of the fragmentation mechanism is really a challenge. And we have currently 150,000 fragmentation mechanisms. So there is actually in the software is all the mass spectrometry knowledge you can use in a second. So you don't need to be expert in a fragmentation, so the software does it for you. Okay, in the future you have heard today about a compound discoverer, so which is connected to MZ Cloud, and next year we will also release a Mass Frontier 8 that will also work together with the MZ Cloud. And last but not least, I would like to thank the following people, because this was work of many, many groups, and I would like to thank you for your attention.